Graphing exponential functions. And what does an exponential function look like? Or what does the graph of an exponential function look like? Well, let's first start with the general form of an exponential function. An exponential function, what makes it an exponential function is it has a variable in the exponent. So the general form would be something like y equals a to the x. And you see how the variable x is in the exponent. That right there is what makes it an exponential function. So that is a variable. Let's see if I can fit it in there. I guess I can. And the a is a constant. And just recall that a constant is simply a number. So the most basic of exponential functions is y equals 2 to the x. And we're going to be graphing that formally in just a second. Again, you can see that we have the variable x, that's the variable, and then we have a base that is a constant base. We say it's a base because it's the base of the exponent there. Okay? Generally, the shape of any exponential function of y equals a to the x, and this is going to be for a greater than 1, looks like something like this. Let's see how I do. It's a nice smooth curve and goes shooting up. You've heard the phrase, it's growing exponentially. Well, that's because as the values of x get larger, the values of y get really, really large. Okay? And if we're of this form, a to the x, and we're not adding or subtracting a constant, then the graph of an exponential function will always, always intersect the y-axis at 1. Of course, this is the x-axis. Why is that? Because, well, what is the coordinate of this point? This is the coordinate 0 for x, 1 for y. And if we replace x with 0 for any number, y equals a to the 0, as long as a is not equal to 0, a to the 0 is equal to 1. Let's see. Let's just do a quick review. 7 to the 0 is equal to 1. 1,563,729 to the 0 is equal to 1. Anything to the 0 power is equal to 1. All right, what's the big surprise behind the pink outline box? Well, it's a better sketch of an exponential function done by a calculator or some sort of graphing device, but it's nice and smooth. But that is the nice general shape of an exponential function where your base is greater than 1. Okay? So let us graph a couple. We'll do a couple of examples here. And the first example we're going to do is the most basic one, like I said before, and that is y is equal to 2 to the x. Okay? So the way we're going to do this, very simple, we're just going to make a table of values. And again, let's just be smart about what we're going to pick. We know that the curve looks something like this because my base is equal to, or is greater than 1. It's 2. So we know that the general shape looks like that. X, Y. I'm going to choose 0 if I can. Love the 0 because when x is 0, okay, then y equals 2 to the x, right? So y equals 2 to the 0, y would be equal to 1. So we have the point 0, 1. Okay, so that gives me the ordered pair 0, 1. And I can go ahead and plot that point. 1, 2, 3, 4, 5. Let's give ourselves some scale. 1, 2, 3, 4, 5. Give ourselves some scale. Okay, so we have the point 0, 1. And there we go. Now, generally, you want to do a positive and a negative. So I'm going to let x be 1. Okay, so let's try that out. Y equals 2, and I'm going to replace the x with the 1, 2 to the 1, and that is equal to 2. So we have the point 1, 2. Okay, and that gives me the ordered pair 1, 2. So let's see, 1, 2, there we go. And maybe I'll try, let's see, -1. Okay, so now we have y equals 2 to the -1. Huh. Well, I'm going to ask you to recall that a to the -m, in other words, a constant to a negative exponent, we can rewrite that as 1 over a to the same exponent, or the absolute value of that exponent, or the positive of that exponent, however you want to think about it. The exponent becomes positive when we move it from the numerator to the denominator. You might be thinking, hold the phone there, Chuck. What do you mean numerator? That's not a fraction. Well, we can always write a number as a fraction by putting it over 1. So we take a to the -m, move it down to the denominator, and the exponent becomes positive. So the same thing here. I can write this as 1 over 2 to the first power, and it becomes positive, and anything to the first power is itself. So at -1, y is equal to 1/2, and that gives me, that's a horrible 2, let's see, 1/2. That gives me the ordered pair -1, 1/2. So let me graph that. -1, 1/2 right there. And there we go. Nice smooth curve going up. You might be able to do like 2 squared equals, ooh, I got lucky, look at that, 2 squared equals 4, 2 to the 2, to help guide you there. What's the domain and range? Well, domain, remember, are all possible x values. Okay? And all you're looking for is anything that you can't substitute for x. And you're looking for somewhere where it'd be undefined, or the square root of a negative number, and because we don't know how to handle the square root of negative number. There's nothing that we can put in for x that's going to make this undefined, or that we're not going to be able to calculate. So the domain is going to be the set of real numbers. So that's cool. Okay. And what about the range? Well, the range, if you recall, is the possible set of y values. Okay, the possible set of y values. Range. All possible. Sorry about my writing. Y values. The pen's not cooperating. Y. What did I write? Abel's. Y values. Okay. All right. So what's going on here? Let's think about this. Well, this graph is going forever and ever and ever this way. So all of the corresponding y coordinates here are going to be taken up. All of these values have y coordinates, and every y coordinate going up to infinity is going to be used. But what's going on down here? Look how I never had this graph cross the x-axis. That's because if I, x was -10, then I would have 1 over 10. If it was -100, I'd have 1 over 100. Oop, I better post the videos. So it will never, ever, ever be 0. Y can never be 0. So therefore, the range is going to be the set of y that is greater than 0. So this exponential function will never be negative, have a negative value, and it will never be 0. Okay, one more example and then we will stop. The graph of y equals 1/2 to the x. Well, I haven't told you what this looks like. I will say it's the same general shape, but let's just take a closer look. Okay, y equals 1/2 to the x. Let's try 0. So let's see, y equals 1/2 to the 0 power. And anything to the 0 power is equal to 1, so I have the ordered pair 0, 1. Okay. What about 1? Okay. Y equals 1/2 to the first power. Well, anything to the first power is equal to itself. So far, so good. Okay. What about negative 1? Okay, y equals 1/2 to the negative first power. Huh. How are we going to handle that? Well, remember, a to the negative m is equal to 1 over a to the m. So my a here is 1/2. So this is equal to 1 over 1/2 to the first power, which is 1 over 1/2, or 1 divided by 1/2, which equals, I'll rewrite that, 1 divided by 1/2. And you might be able to do that in your head. You should be able to. But if not, 1 divided by 1/2 is equal to 1 times 2 over 1, which is equal to 2. So for negative 1, y equals 2. And we have the ordered pair negative 1, 2. And we have the ordered pair 1, 1/2. Let's go ahead and plot those. 1, 2, 3, 4, 5. Give myself some scale. 1, 2, 3, 4, 5. There we go. So we have 0, 1. Ah, there's that point again. 1, 1/2. Well, that's a little different than the other graph. And negative 1, 2. Huh. Well, I will tell you that when the value of a is between 0 and 1, the general shape of an exponential curve looks like that. It reflects or flips over the y-axis compared to when a is greater than 1. Okay? So greater than 1, it will always look like this. And between 0 and 1, oops, I went the wrong way. Between 0 and 1, it will always look like this. The domain and range are going to be the same for the same arguments. The domain is a set of real numbers, and the range is a set of y greater than 0. Okay, hope you enjoyed it. We will see you next time. Becker is out!